Good morning, people. Mr. Carver here. Today we're going to do section 3.7, optimization. Now, you did problems like this back in pre-calculus and in Algebra 2, so let me give you an idea of the problems that you're going to be solving today. All right, problem will look something like this. The sum of a first number and twice a second number is 100. Find the numbers such that their sum is a maximum. Actually, it's not a sum, it's a product. So let me change that. That's their product is a maximum. All right. So let me give you some steps that you're going to use in section 3.7. You can use this for every single problem that you do. And then we'll work through this problem as I write down the steps. So step number 1 for solving optimization problems is as follows. So step number 1 is find the equation to be optimized. And that is, find the thing that you're trying to find the maximum or the minimum of. So if I look here at this last statement in this problem, find the two numbers such as their product is a maximum. I'm trying to maximize the product. So just like we did back in Algebra 1, let's start off by defining our variables. Let's let x equal the first number. You can use whatever letters you like, and let's let y equal the second number. And again, the letters don't matter. You can reverse them. It makes no difference. You'll still be able to find these two numbers. So what I'm trying to do is maximize their product. If you recall, product is an answer to a multiplication operation. So I'm going to just use P for product. And this is x then times y. And this equation is what I'm trying to find the hilltop in, because I'm trying to find a maximum. Now, the problem with this is, if you think about how you found maximums or minimums back in the earlier part of this chapter, we only had two variables. You generally had y and x, and you were trying to find a relative max or a relative min. If you have three variables, that's a problem, which leads us into step 2. All right, you can pause and write that down if you like. Step 2 says, if you have more than two variables, find a second equation and use substitution. And we're going to use substitution to get rid of one of those variables. Now, the second equation comes from the first part of this problem. It's this portion right here. And it says the sum of the first and twice the second is 100. So just like we did back in Algebra 1, the sum is the answer to an addition operation. So I've got x plus then 2 twice the second, which is 2y, is equal to 100. Now, I'm not doing calculus on this second one. I'm only going to do calculus on the one inside the red squiggles. All right, now, I'm going to use this. It looks like x is the easiest to solve for if I subtract 2y from both sides. So I get 100 minus 2y. And what I'm going to do now is I'm going to take this portion right here, and I'm going to put it into my product equation for x. So then I'll just have two variables. I'll have a p and I'll have a y. Now, when I do that, that's going to give me then this equation right here. The product, the product is equal to, x comes out, I put in 100 minus 2y, and I multiply it by the y that's there. I'm just using substitution. Again, I still want to find the maximum of this equation right here, but now I can do that because I was doing it back in the earlier part of chapter 3. All right, now that brings us to step 3. And step 3 is to use calculus to find the maximum or the minimum. Now, it'll depend on the problem whether you're finding a hilltop or a valley. In this case, I'm looking for a hilltop because it's a maximum. So this, from here on out, it's really nothing different. I'm going to take this, again, this problem right here, and I'm going to start doing calculus to it. All right, now in order to find the maximum of that product equation, what I want to do is find critical numbers. And if you recall, we're going to find critical numbers by deriving and setting it equal to 0, the top, and setting it equal to 0, the bottom. Right? Now, I want to get rid of this product before I do it because I don't like the product rule. Generally, actually, it's just easier to do it without the product rule. So if I distribute that y, I get 100y minus 2y squared. And now I want to derive it because I'm trying to find critical numbers. 100y goes to 100, 2y squared goes to 4y. This is over 1, so it's not undefined anywhere, but it's certainly equal to 0 where the top is equal to 0. So I set the top equal to 0 and solve. Divide by 4, y rather equals 25. So that's my critical number, which brings me then to the last step. This is step number 4. And step number 4 is to prove your answer, and you're going to do that just like you did back in chapter 3. I'm going to take my pen, I'm going to make a number line, I'm going to put 25 on it, and I want to prove that 25 is in fact a max. So what I want to do is just pick numbers on either side and plug them into my slope machine. So I've got p prime of 1 and p prime of 50. So I'm going to take those and plug them right into here. Now, if this is indeed a maximum, I want it going uphill on the left. So if I plug 1 into y, I get 100 minus 4. That's definitely positive. That means it's going uphill. Now, if I plug 50 into my slope machine, I get 100 minus 200. Definitely negative, which makes this thing right there a maximum. So that means y is equal to 25. My second number is equal to 25. Now you just got to find the first number. And what we're going to do is we're going to go back to the equation that I did not use calculus on. And that is right here. Or here. Either one of those. X plus 2y is equal to 100. Or x is equal to 100 minus 2y. And my y is 25, which means my x is 50. Now you don't need to prove that. You've already shown that 25 is a maximum. So the assumption is if y is 25, x is 50, those are your two numbers. No more work needed. You are done. All right. Let's do another one. All right, so try that on. I'm going to read it. You can pause this if you want to take some time to put it in your notes. But a box has a square top and, a square bottom and no top. If the box has a surface area of 108 square inches, find the dimensions of the box which maximize the volume. All right, let's start off with a drawing of the box. All right, something like that. It's got a square bottom, so I've got that x times x. Those dimensions have to be the same. And the height does not necessarily have to be equal to the base, so I'm going to use a separate variable. We'll call that y. All right, so now let's start off with the equation that I need to maximize. And that is, in fact, the volume of this box. So it looks like my volume is equal to, what is that, length times width times height, or the area of the base times how tall it is. The area of the base is x squared, and it is y tall. So x squared times y is my volume. And by the way, this is what I want to maximize. Just like in the previous problem, though, this has too many variables. I've got a v, an x, and a y. So now I need a second equation that's going to allow me to get rid of one of these. And I think it comes from this part right here, the fact that the surface area of that box is 108 square inches. So let's talk about the surface area of this box. If you look at it, it's got 4 sides and a bottom, right? There is no top. So the 4 sides are all rectangular. And we can write those as, let's see here, that is x times y, and there is 4 of them. Plus I have then the area of the bottom, which is x squared, and I know when I add all those together, I get 108. All right. Now, I need to solve for either x or y. Solving for x is difficult because it's a quadratic. However, I only have one y, so I think I'm going to solve for this y right here. All right, so first I'm going to take away x squared, so I've got 108 minus x squared, and then I'm going to divide everything by 4x. So I got y is equal to 108 minus x squared all over 4x. And now what I want to do is I want to take this, and I'm going to plug it into my volume formula for y. All right, and then I'm going to use calculus to solve and find out where that has a hilltop. So let's go ahead and continue on here. I've got volume then is equal to, it looks like I've got x squared, and then I take my y out and I put in 108 minus x squared all over 4x. Now, I got to find a critical number of this thing. It looks horrible, right? I've got a product, and within the product I have a quotient. So let's clean this up and see if we can eliminate both of those things. So stick with me here. I'm going to first cancel these x's. So I cancel one x here and the other one on the bottom. And then what I'm going to do is I'm going to bring the 1/4 out to the front and distribute the x. So see if this makes sense. I've got 1/4 all the way out to the front, and that'll be then times 108x minus x cubed. So again, what I did was I brought the 1/4 out front, and then I distributed the x to both of those. Now, the nice thing about this is I have a product, but the 1/4 is a constant, so it's really easy to derive. It's the constant multiple rule, and then inside there, those are really easy to derive. So I've got v prime then is equal to 1/4 out front. Remember, constants do not derive, they just stay there. This is times 108 minus 3x squared. All right, now, in order to find critical numbers, I set this equal to 0 or find out where it's undefined. Well, there's only a 4 on the bottom, so it can never be 0. So now I just deal with the top. I've got 0 is equal to 108 is equal to 3x squared. 3x squared is equal to 108. I divide by 3. That's x squared is equal to 36. X is equal to plus and minus 6, but I get rid of the negative 6 because you can't have a box with a length of -6 for a side. All right, so I've got a critical number of 6, x equals 6. Now I just have to prove, if you recall, that my final step, prove that that is in fact a max. So let me clean some of this stuff up. You can always rewind if you need to look at it again. And I'm going to keep my derivative because I need to make a number line, right? I'm going to put 6 on it. I'll test 1, and then I'll test 10 billion. Numbers on either side of 6. I plug in 1 into my slope machine, which is right here. I get 108 minus 3, definitely positive. 1/4 of that is also positive. This is looking good. Now I plug in 10 billion. 108 minus 3 times 10 billion squared. Let's see, carry the 1. Yes, that's negative. That means this is in fact a max. Goes uphill to the left, downhill to the right. So x equals 6 is my first answer. I'm going to go ahead and box it. Now remember, what I want to do is I want to go back and I want to solve for y by using the equation that I did not use calculus on. That's this thing right here. All right, so my x is equal to 108 minus, what is that, 36, all divided by 24. 108 minus 36 is 72, divided by 24. X is equal to 3. So it is a 3 by 3 by 6 box. 3 by 3 by 6. That is wrong, 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 wrong. It is a 6 by 6 by 3 box. Because x is 6, y is 3. Good morning, Mr. Carver. All right. That's what I'm looking for on the test. Let's do one more before we get out of here. All right, I want to find the point on square root of x plus 2, which is closest to the point 30. So let me draw you a quick picture here. Square root x plus 2 is shifted 2 to the left, just like we did back in the day when we did 5,000 of those in this class. The point 30 is right here. And what I'm looking for is the point on this square root curve that's closest to that point 30. So it looks like, if I was just to guess, maybe somewhere like right there. And that's what I'm looking for. Now, what I need to know is I need to know that point which minimizes this distance right there. So the thing I need to minimize in this case, I want to minimize the distance formula. If you recall from Algebra 2, this is the distance formula. D is equal to the square root of x1 minus x2, the quantity squared, plus y sub 1 minus y sub 2, the quantity squared. I know it's horrible, but really it's just the Pythagorean theorem solved for C. I don't know if you knew that before, but anyway, so what we're doing here, we're trying to minimize this thing. So I'm looking for a valley in that curve. The trouble with that is I've got way too many variables. I've got D, we have 2 different types of X's, 2 different types of Y's. I really have like 5 variables here. So what that means is I have to use something else. I have to use substitution to get rid of some of that. Well, how about this? I know that there's a point 30. The 3 is an X, the Y is a 0. So I can at least get rid of some of this stuff. So I have D is equal to the square root of, let's put 3 in there for X. And I'll put 0 in for Y. By the way, it doesn't matter if you put it in for X1 or X2. It makes no difference. That's 0 minus Y sub 2. And by the way, now I just got rid of the sub 1 or the sub 2's. It doesn't make any difference. You can keep them on there if you like. I still have too many variables, right? I have a D, X, and a Y. How about this? f of x is really just y, isn't it? So y is equal to root x plus 2. I think I can get rid of this. So I now have d is equal to the square root of 3 minus x, the quantity squared, plus 0 minus the square root of x plus 2, the quantity squared. All right, that's better. Still kind of looks horrible, so let's go ahead and clean this up here a little bit. And now I have d is equal to the square root of, let's see, let's go ahead and FOIL this out. This is 9 minus 6x plus x squared, right? If I FOIL that out, that's what I get. And the second, if I FOIL this out or just square everything in there, I get positive x plus 2 because the square roots cancel. This gives me then the square root of, what is that, x squared minus 5x, that looks like plus 11. All right. So now what I'm looking for is a valley in this graph right here. Now, in order to find the valley of this graph, I need to find critical numbers. All right, so check this out. What I'm going to do is derive. And while I'm at it, I'm going to rewrite this, because check this out. I'm going to use the chain rule. I know, all this stuff. So this is really to the 1/2 power. So my d prime is going to be equal to 1/2 x squared minus 5x plus 11 to the negative 1/2 times 2x minus 5, right? So first I do the outer, and then I derive the inner, and multiply them together. All right, so now, let's go ahead and make some room here. So my d prime then, if I were to write that in fraction form, I've got a 2x minus 5 on the top, and I have a 2 on the bottom, and the square root of x squared minus 5x plus 11. All right, now I'm going to save you just a little bit of time here. I'm going to tell you this. Critical numbers come from the top and the bottom. So I have a critical number from the top at x is equal to 5/2, right? If I set the top equal to 0. Now if I set the bottom equal to 0, you could take my word for it, you're going to get an imaginary number. So I will guarantee you this. If I give you these types of problems on a test or a quiz or on the homework, critical numbers for a distance type problem, you will never get critical numbers from the bottom. All right? So that means in this case, I just have one critical number, 5/2. Now I just need to prove it. So I'm going to test 1 and I'm going to test 50. And I'm going to plug this into d prime. So I plug 1 into the top, that gives me a negative, and the bottom, remember we're only looking at real answers, I should say, so something that gives you something that's not imaginary. So if I plug 1 in the bottom here, this is 1, take away 5 plus 11, that's definitely positive in there. So the top is negative, the bottom is positive, this is minus. Now if I plug in 50, I get a positive on the top, and I also get a positive on the bottom, which is exactly what I need. This is a minimum. Going downhill to the left, uphill to the right. Now all you have to do is find y, and in order to find y, I'm going to go to the equation where I did not use calculus. So it looks like my y is equal to the square root of 5/2 plus 4/2. That's the square root of 9/2. And what's amazing is, that's actually where I drew this. Check this out. There's 2.5 on the x right there. And that's exactly where I drew it. And then this right here is square root of 9/2. That's incredible. That doesn't normally happen, but it did in this case. All right, so there you go. Your point on this curve turns out to be 5/2 square root of 9/2. All right, guys, I hope that's enough to get you through the homework. Certainly, I will help you as much as I possibly can. Have a great day. Thanks.